I would like to introduce our first speaker, Gabe Yu, who is doing capturing discrete choice and deliberation time endogenously using sequential sampling and accumulation-to-threshold principles. And as he gets his slides set up here, I just want to underscore that one of the fantastic things about his work is that it really takes the examination and a close look of how to model decision time in a way that is theoretically adequate in a model. So I'll let you introduce yourself and just take it away. You have about 15 minutes.
Great, awesome. Thanks, Lisa. Let me just share my screen really quick. This one. Cool. And here. Yeah, so yeah, thanks, Lisa. Hi, everyone. So my name is Gabe Yu. I'm currently working as a senior system modeler at Econ. It's an infrastructure consulting firm. And one of my major aspects of my work involves modeling human behaviors and their interaction with the built environment for supporting infrastructure and land use policy and investment decisions. So I'd like to use this opportunity to share a connection I realized between the techniques used in the system dynamics and those used in the cognitive and mathematical psychology when I was testing the potential of capturing the impact of variable decision times on the sequence of major investment decisions. We know that the field of system dynamics has been studying and implementing information and perception delays for a long time. In fact, it is considered one of the major strengths over other modeling paradigms in terms of its clear assumption about how delay may vary endogenously. However, there seems a missing set of techniques for capturing the delay explicitly caused by deliberation in system dynamics. As we know, some major discrete choices such as merger and acquisition, infrastructure decisions, and household and car purchase may lead to path-dependency and cannot be modeled by just simply averaging or smoothing out using smaller individual decisions. In those type of decisions, it is possible that the delay tends to be longer when decision is harder, which leads to the tendency of receiving additional information during the deliberation, which in turn leads to the change of preference. This type of endogeneity cannot be really captured using fixed or exogenous delays. Adding even more complexity is the various levels of time pressure when making the decisions. On the other hand, in the field of cognitive and mathematical psychology, sequential sampling principle has been a dominant macroscopic approach in modeling discrete choice and its corresponding delay for a few decades. This family of models, I would say, are typically backed up by empirical and experimental data and can be seen as useful summary models from those that model individual neurons or an important benchmark model for developing high-fidelity models. This underlying idea is actually quite straightforward. People may have limited cognitive capacity, and the information is usually processed in chunk unless it's extremely simple information or decision problem. We can represent this using a stock flow diagram. When we use the inflow to represent the process of the decision of a decision maker to collect and process information piece by piece instead of in a single chunk. Another major principle of cognitive and mathematical psychology modeling discrete choice and its corresponding deliberation time distributions is the accumulation-to-threshold principle, which is closely associated with the sequential sampling approach by answering what the decision maker would do with this stream of quote-unquote stream of information. It is typically assumed that during the sequential sampling, the evidence will accumulate from an initial point, which may or may not be biased due to prior decision or information. Once the accumulated evidence reaches a certain threshold, a decision can be triggered. Since most of the model utilize the accumulation-to-threshold principle, considers a random term so that the final decision is a stochastic. I added the term stochastic to emphasize this nature. in front of the accumulation-to-threshold, this term. If we use a stock variable P for preference state and using tau as a time step size, its change is influenced by both the deterministic components delta P, and and also the stochastic components epsilon. When the state preference P reaches a upper bound theta, and option 1 is chosen. If it reaches lower bound minus theta, the option 2 is chosen. Otherwise, the subject will just continue sampling information and accumulating evidence. So we can actually plot the simulation instances for a binary decision when viewing the preference state as a stock variable, as shown on the left. As shown on the right, the stock level starts from an initial position, which may or may not be biased. Then it accumulates until the upper bound or lower bound or upper threshold or lower threshold is reached. We can run many simulations to obtain the distribution for option 1 and option 2, and it's possible that the distribution for each options may be different. The practice or the tradition in mathematical and cognitive psychology of using the sequential sampling and the stochastic accumulation-to-threshold principle to model preference and deliberation time simultaneously in the past several decades can really be quite neatly understood and summarized using visualization and modeling techniques commonly used by the system dynamics field. Next I'll dig deeper into some of them to demonstrate the point. Near the end of 1970s, Professor Ratcliff proposed a diffusion decision model where the accumulation is a additive process with a random starting point and a random drift rate in addition to the random noise component, epsilon. Note that there's no feedback, from the accumulated evidence to its own inflow if we show this in a stock flow diagram. The time pressure due to rigid deadline can be captured by a vertical decision boundary, where if the preference state does not reach the threshold, the decision maker will simply make a decision based on whether it's positive or negative relative to the neutral point. The time pressure due to a internal or external instruction of making the choice soon or rapidly can be captured by adjusting the horizontal inhibitor threshold or decision boundaries. One major testing criterion he and his team has been advocating is that it is highly falsifiable in terms of because the empirical data not only need to match with the preference distribution but also the response time distributions for each potential options, which I agree. In 1992, Professor Busemeyer and Professor Townsend proposed to use a very similar mathematical model for capturing the quote-unquote value-based binary decisions and the risk, and it is used mostly in the setting of gambling. Two main extensions from the diffusion model. First, they interpreted the drift rate as the value-utility difference or utility difference between two options. The bias risk preference is captured through the utility itself. Second, they introduced the feedback. When the feedback is positive, more preference towards one option leads to more preference. And third, they slightly less important is that they introduced approach avoidance behaviors to capture a similar idea now commonly known as loss aversion. So we can notice that we just want to highlight that there's a key difference that the state preference state can feedback to the inflow. They also call it valence. So from the perspective of general stochastic process, Ratcliffe's binary decision diffusion model can be essentially seen as a linear process or one-dimensional Brownian motion, while Busemeyer and Townsend's binary decision diffusion theory, or DFT, is essentially an Ernst-Uhlenbeck or OU process. In 2001, a so-called Leaky competing accumulator model was proposed by Usher and McClelland. They proposed that for an alternative decision, one can consider each alternative as a separate accumulator, and their changing rate may be influenced with one another in terms of the stock variable. Here is the preference state. Also around that time, a multi-criteria DFT or multi-criteria decision field theory was proposed, which was also inspired by Usher and Zake's 1993 paper on a network-based model along with other innovative features. Later, it was expanded by considering more than two alternatives, but the general process or the idea can be seen as 4 phases. The phase 1, the decision maker evaluates alternatives by weighted feature with certain attention weight. And in the phase 2, different alternatives are captured with each other. In phase 3, the evidence or / valence are accumulated in an additive manner. And the phase 4, the decision maker decides, or the modeler, the model itself decides if the decision is triggered by because it's surpassed the threshold or not. If one alternative reaches the negative threshold, that particular alternative will be dropped, which is a similar idea proposed in the elimination by aspect theory proposed by Tversky in 1970s. As we probably noticed from the broad view above, mathematically, it can be argued that in essence, all of those models can be described in this format. What people in the mathematical psychology and cognitive psychology have been really arguing in the past few decades are really about the 3 interrelated components. Note that the changing any of the parameters or model structure here using the sequential sampling and the stochastic-accumulation-to-threshold principles will simultaneously change the preference and response time, which gives it's challenge, which is a major challenge, but also an opportunity for this type of model as a very highly falsifiable model. The sequential sampling and stochastic accumulation-to-threshold principles may be useful tool for system dynamic modelers' arsenal. On the other hand, it seems natural that there's system dynamics techniques, modeling techniques, can also have some potential to contribute to the current system sequential sampling and the stochastic accumulation-to-threshold models currently used in cognitive and mathematical psychology. Here are at least 5 major categories of generalization that I realized, and I will dig deeper slightly in the next few slides. The first generalization is the simple combination of commonly used techniques for modeling perception delays in system dynamics. This way we can explicitly consider the perception delay and the deliberation delay. The second generalization I'm proposing here is the endogenous decision where the threshold is influenced by time. This is a new compared to the existing approaches using the fixed or endogenous delay. The upper right profile is here. I just want to mention this. So the state whether it's triggered or not is also influenced by the state preference itself. On the upper right here is the profile that I generated in a presentation and / article that I proposed in about 2 years ago, where you can see the decision boundary is influenced by the state preference endogenously, as compared to Hawkins' paper, where they're also having a collapsing decision boundary, but it's exogenous. It has nothing to do with the decision with the state preference itself. The third generalization is about modeling time pressure. Currently, the two, as we just mentioned, currently 2 major approaches are adjusting the vertical or horizontal decision boundaries. Here, I propose that the update frequency can be considered as a parameter in modeling time pressure as well. In fact, I think that this method might have some homeomorphic connection with how cognition actually works. Indeed, it does not sound very strange, as people sometimes indeed consciously or subconsciously tell themselves to think faster when under pressure or think slower when making very important decisions. In here, by faster, I mean people may sampling and accumulating evidence more intensely than otherwise. As the fourth generalization, I suggest that the accumulation might be actually in higher order manner, especially for more complex decision problems. And another motivation here for proposing this generalization is that it's well known in the cognitive psychology and mathematical psychology that the shape of the decision distribution is very rigid. So higher order delay may help capture more different shapes of deliberation time distributions for each alternative in a decision problem.
We have about less than 1 minute left.
Okay, well, I'm almost done.
Perfect.
Okay. The final generalization I'm proposing here is about capturing the influence of a sequence of highly related decisions. Professor Hyland and Michael Hyland at UC Irvine and I apply this approach to modeling people ordering mobility and demand services such as Uber and Lyft, where a user needs to go through multiple steps in order to order a ride. We can pull a few simulation instances to illustrate the process of so in this process there's more than one decision or you can call it sub decision for this. For more details, please refer to our paper published on the Translation Research Part C Emerging Technologies last year. And then in summary, the system sequential sampling and the stochastic-accumulation-to-threshold principle may be useful techniques for system dynamics modelers arsenal. And then the models that are considered very different in cognitive psychology are actually very similar models from system dynamics perspective. I think this can encourage more constructive discussion in that field, allow clear identification of assumption difference, and also whether all those assumptions that they're arguing are really fundamental or not. And system dynamics techniques such as high-order delay, aging chains, cold flow, and trend perception may contribute to the field of cognitive psychology as well. So I really appreciate listening. Thank you for your time.
Thank you so much. That was wonderful.